Good afternoon, and good morning, and good evening. So welcome to the 48th ASE seminar, Advanced Supercomputing Environment. My name is Kengo Nakajima. I'm a faculty member of the University of Tokyo Supercomputing Center. So before starting the seminar, I just briefly overview the history. Okay. So this ASE seminar series was started by my old colleague, Professor Katagiri. So he's now in Nagoya University. So this guy. Okay? And so this seminar is held irregularly. Okay? So when we have a domestic or international visitors to the Information Technology Center, we have this type of seminar. Okay? And official language is not fixed. Today it's English. Okay? And the first seminar was on March 3rd, 2008. So it's 16 years ago. So any topic related to HPC and supercomputing. And the last meeting before COVID-19 was the 40th on February 4th, 2020. And we have one full online meeting, February 4th, 2022, 2 years after that. And the first hybrid seminar was the 42nd on April 11th, last year. Okay, so now, today is the 48th. And so today, we are happy to invite the guest speaker, Dr. Arnab Kumar Paul. He's an assistant professor, and so from the Bora Institute of Technology and Science, Pilani. It's a BITS Pilani, India. So he's a co-organizer of the WaitIO 24 workshop in conjunction with the IEEE Cluster 2024 in Kobe next week. And so that's why he's visiting Japan, and so we are happy to invite him to our seminar. So this is an overview of today's program. We start with the invited talk by Dr. Paul. And so we have three related talks by my colleagues, so such as IO and system software. And so then close the session. Okay. And the invited talk is 40 minutes, including discussions. And our talks are 25 minutes, including discussions. Okay, so please keep muted during the talk. And if you have any question, you can turn on your microphone after the talk. Okay, so before starting the talk, I would like to briefly overview. So Arnab Paul is an assistant professor in the Department of Computer Science and Information Systems at the BITS Grad, India. So he leads the Data System and High Performance Computing Lab, like the Dash Lab, at the BITS Grad. Okay. His research interests include HPC, parallel file system, SysML, so the distributed systems, and edge computing. Before joining BITS Pilani, he was a postdoctoral research associate at the Oak Ridge National Laboratory, USA. And he completed his PhD in Virginia Tech. And so he routinely published the top tier conference, IPDDS CC3, Cluster, PPDS, and DMS. So he is a co-general chair for IPC 2024 in India, and also a part of the storage workshops of the Cluster in IPDDS. Okay, so please start. So let's welcome our speaker.
Thank you for the introduction, Professor Kengo. So hi, I'm Arnab. So I'm an assistant prof at BITS Pilani, Goa campus. So it's also a pretty old, like it's considered to be of the same tier university in India as IITs. So, but it's a private institution. So, so a little bit about myself before I start my talk. So I joined BITS Pilani in December 2021. Prior to that, I was a postdoc at Oak Ridge National Laboratory, USA, for a little bit more than 1 year. So it had to be cut short because of COVID, and I had to return back to India. So I completed my PhD from Virginia Tech, US. So I was under the assistantship, under the mentorship of Dr. Ali Bhatt. So there I worked on parallel file systems as well. My research interests have been in HPC, storage systems, file systems, distributed systems, systems for machine learning. So Dash Lab, as Professor Kengo mentioned, I started Dash Lab at BITS, and these are the QR codes of Dash Lab and my homepage. You can go through those. Okay, so today's talk is about mitigating IO bottlenecks for HPC applications. So I'll be covering two topics here. One is how are IO bottlenecks mitigated in parallel file systems. So since I'm a parallel file system person, so I'll talk about that first, and then about one of my work that I started during my postdoc, which is on the systems for ML, right? How are IO bottlenecks being mitigated for distributed deep learning applications? So there are two things that I'll be covering. So the first one is an adaptive end-to-end IO load balancing framework for large-scale parallel file systems. So this was published in this year's ACM TOS, and this is with my collaborators at JU Mainz, Germany, IBM Research, and Oak Ridge. So this has been like we worked on it for 2-3 years because of these international collaborations, right? So it took time, but okay. So before I start this, let's look at a typical HPC IO stack, right? So at the application side, at the client side, we have the IO libraries, we have MPI IO library, we have the MPI, we have the client side APIs for all of these parallel file systems, right? The POSIX and all. And then there are these IO forwarding layers, which try to club a lot of small reads, a lot of small writes together to make one bigger write or one bigger things, right? And then these are forwarded to the parallel file system, right? So this is how like a typical IO stack looks like. That's what we have here as well, right? In the in University of Tokyo systems as well. So we have all of these object storage servers. You have the fast file system and the slower file system, right? So there will be all of these storage servers, the storage targets, and you will have a parallel file system on top of it. So the Lustre parallel file system. So again, this parallel file system is what I have worked on for this particular work. And this parallel file system is also part of your supercomputer at University of Tokyo. So the architecture is very simple. Like you have all of these Lustre clients. There are the management servers and the metadata servers, and you have the object storage servers and the targets. And all of these are connected using InfiniBand and all, right? And there's the LNet, like the Lustre networking protocol that connects these networking components, right? So one of the important things that these parallel file systems give, right, is the capability of file striping. So a brief about how file striping works. So when you create a file, right, so by default in Lustre, the stripe count is 1 and the stripe size is 1 MB. So what that means is that whatever file you create, it will go to one particular target in stripes of 1 MB, 1 MB, 1 MB. Okay. So now, and that's the default, and very few people actually do changes to whatever the default striping configuration is, right? For example, in the IBM Spectrum scale, the stripe count is 1, but the stripe size is 16 MB. So that means a 16 MB chunk is going at one particular time to a target. So this is just an example of how file striping in Lustre is working. So the default, so for example, say we have file A, the stripe count is 3, okay? And the stripe size is 1 MB. So what that means is we have 3 targets, OST0, OST1, and OST2. That means 3 hard disks or 3 SSDs, whatever, right? So this 1 MB chunk of each will go into these 3 targets in a round robin fashion. Okay. So, and that's very important because round robin is sometimes bad, as we can see here, in the sense where file C says that, hey, I want to create a stripe of 1, but the stripe size might be 16 MB. So as you can imagine, this round robin fashion would create some sort of a load imbalance, right? It's going like 1, 2, 3, 1, 2, 3, 1, 2, 3, right? The new file comes, again, it goes to 1, 2, 3, right? So there's a round robin kind of file strapping strategy that Lustre file system operates. And how are the clients interacting with these stripes? So what happens is at the client side, it says that, hey, I want this particular file. It goes to the metadata server. So the file open request is generated, right? A POSIX call is generated with open. And then it goes to the metadata server. The metadata server looks at where are the objects placed on the targets. It gives the object IDs to the client, and then the client uses those object IDs directly to read or write to those particular targets. Okay, so without having the metadata server, without interrupting whatever the metadata server is doing. So what that means is this, at the file creation time, we need to be very, very smart as to where the file should be created, where the stripes should go. And that's what this work was all about at the file creation level. So Lustre, in its, I think in the 2018 version, came out with this progressive file layout feature. What that means is you would have, like, as the file increases, you have different number of stripes. Okay, because if you have a 1 terabyte file, it doesn't make sense to have a file stripe of 1. Whereas if you have, say, a small file, a 1 MB file, it makes very good sense to have 1 as your stripe count, right? You shouldn't need to break it down into more smaller chunks, right? So that's what progressive file layout brought about. So as and when the file increases, you can say that, hey, from 0 to 128 MB, I want just 1 stripe. Whereas if it goes from beyond 128 MB to 512 MB, I want it to be distributed across 3 targets. Things like that, right? So, and this is a configuration file that we use. So when when a user is this is an IOR, like as you can see, that's basically /MNT/Lustre/IOR in this this one. I don't think it's visible at the back, but it's basically a set stripe command that is used to specify, right? And that specifies how much like this entire thing, the picture in command form is this, right? And that's the JSON file that we basically parse that, and we make it into a JSON file, and we use it for our tool. So what we saw is we ran IOR and HackIO. These are very popular benchmarks. So HackIO is a cosmology code benchmark. So we ran this in a file per process fashion. And there were, like, we ran it on 35 object storage targets. And what we saw is with the default Lustre, the round robin fashion, right? There was a considerable load imbalance when you are running it, right? for IOR as well as HackIO. We did a file per process. We did single shared file. We increased the number of processes. For everything, there was this load imbalance. Same, there was a load imbalance for PFL, which is progressive file layout, right? So now our major thing was this load imbalance is actually creating a read or write performance imbalance as well, because there is load imbalance on the targets. So our major thing was, can we do something that would have a load balance, right? And a major drawback that Lustre had was it wasn't looking at what the current load on the targets was. It was just doing it in a round robin fashion. And so I think in around 2018 or 2019, Lustre made another allocation strategy, which was called the weighted random allocation. So if there was a huge difference in the load in the object storage targets, it would assign randomly instead of round robin fashion, with a higher weight given to a lower, like a lower loaded disk, right? To make it at the same level as loaded ones. So now that means, and we compared it with all the approaches and we saw that there was still load imbalance. So we came up with something like this. There were a lot of components that we designed, right? So let me go through each a little, like not to go into too much detail. So the first thing that we were doing is when an application first runs, we record what the application does, right? So that when the application runs again, we can make some intelligent decisions based on profiling that application, right? So we used, so there was a tool already, Recorder, which records all the IO activities of a particular application. We made changes into it because our major thing was we just wanted to record the create and the write requests, because reads are anyways buffered, right? Reads are anyways cached. So it doesn't hit the parallel file system that regularly as create or write. So we changed it a little. So this is how, like, we were looking at the IO library of, like, we looked at H5 create, we looked at file open on the MPI side, and also the POSIX level. So we transparently intercepted all of these, and we were creating a trace for every application at the create side, right? So then we would parse this trace, right, for an application, and we would try to make some sort of predictions, in the sense when the application runs next, right? We have the application ID, we have the user who submitted that application, and we also have the file name that it wants to create. So based on its past history, right, we can say that, okay, this particular file, this is the size that it would take, right? This particular file, this is the size. So because at the creation step, we have no idea of knowing how big the size is. So that's why we were profiling it before. And as I already showed you the PFL configuration file, we were taking it. So if someone is using PFL, it was not needed. It was not mandatory. So if it's not mandatory, then people would be using like the default striping config of 1 and 1 MB. And if they were using it, we were parsing that and we were storing it in a JSON file as this. So now what happens is we have the prediction model, which would say this file request has come to create. This is what the file is supposed to be like, right? This is how much size it's supposed to be. This is what the application user is saying, that if this is a PFL config or if this is a default Lustre config. Now, all of this is fed into some interaction database, like some database which takes all of this information. How much is the stripe count? How much is the stripe size? What's the file name, right? And all of these are happening at the client side. So there is no, like, nothing needed at the server level. So at the server level, the only thing that we needed were the statistics, and we were using Lustre API for getting those statistics. So we were getting the statistics of the metadata server, we were getting the statistics of object storage servers as well as the object storage targets. And these we were getting like every 5 seconds, every 10 seconds, depending on whenever the servers are free, whenever there's not too much of things that are happening. And we were mainly concerned with how much the server load is. So server load is more about the CPU load, the memory load, because all the requests would go through the server. From the target, the storage target, we were mainly taking how much capacity is available, right? The capacity, only then we would know where to place the file. And on the metadata server, we were just looking at like when the metadata server is free, so that we can run our allocation algorithm. So that's primarily what this entire architecture was. Like there were a lot of bits and pieces that we did, and we tried to form a pipeline of all of that, right? And with very, very minimal things that we needed at the pseudo side. So what we did was we took everything, all of these. So at time t, what do we have? At time t, we have the past, like the current application requests. Like say there are 100 applications that are running on the supercomputer, and those 100 applications have given some sort of create requests for me to create a file, right? And I also know what kind of future requests are going to come from those applications based on my prediction model, because those applications had already run before, right? So now with taking all of these file requests, the file create requests, the current ones that are already there, as well as the predicted ones, we run this min, flow, max cost kind of algorithm, right? And as you can see, the edges, like we are trying to maximize the OSS cost, and we are trying to say that like one particular stripe, like if say a file is supposed to have 3 stripes, the 3 stripes should go across 3 storage servers, not 3 storage targets. It should go across servers, not just targets, right? So things like that, we used these, and we saw that like this was a very scalable kind of graph allocation model. Like it would hardly take a second to just do this with 1,000 requests, right? So, and we would run this only if our prediction had gone wrong again, right? So this is what we would have, and then we would give it like whatever the OST allocation algorithm was, we would give it back to the client. So now the client knows if this file is coming to me, if this is the file name that is coming for this particular application, I know which are the object storage targets this should go to. So, and that was the placement library that we had. So that also we used LD preload and all of those kinds of interceptors to place the file to those OSTs, right? So, so running our Tarazu. So Tarazu in India, like in Hindi, is basically a balancer, right? Like in the shops, you have the kgs and the load, right? So that's basically the Tarazu system that we call in India. So we said that, okay, that's a good name to give for the system which tries to balance the load. So we were comparing Tarazu with LSA. So LSA is the Lustre striping allocation, which could either be the round robin thing or the weighted random thing, whatever Lustre uses during that time, right? So based on our experiments, if you see that these 35 OSTs, the middle line is what is Tarazu. So as you can see, when IOR ran, so this is with the IOR with 16 processes, 32 GB file, 128 GB file per process. It was like Tarazu gave a load balanced kind of a setup, as well as it gave even better when we were looking with PFL. PFL is much harder to solve, right? Because your striping counts keep on differing as you go higher in the file size. So with this, we saw, so here I am not giving all the graphs and everything. So with this, we saw that the read performance that Tarazu got, right, was like before with just Lustre striping default, it was around 625 Mbps, but now it gave us 825, right? So around like 30% increase of whatever Lustre default would give. So there was a significant read performance, and it was only because now the stripes were across multiple servers. So each server was not getting choked by one particular file's request, right? It was across servers. So the ports were not getting blocked and all. It was across racks, and we could have more intelligence into this, right? By going across racks, by going inter-rack, what should go inter-rack and all of that. So this was only looking at across servers. So so that's what I wanted to talk about. I wanted to keep it short, not going to too much detail of one work. So the current work that we are trying to do is with regards to BGFS. So in BGFS, there is no concept of this progressive file layout. It's a default, whatever the striping config and the stripe count is, right? So now here in this Tarazu work, we had looked at the striping for the entire application, right? So like if someone is setting the striping configuration, that is for the entire application. So now in BGFS, the current work that I'm trying to do is like, can we do the striping per file? So let me give an example. So an application, when it runs, right, it, for example, say creates a lot of small files in the beginning. Maybe those are library files or whatever, right? And those files are typically in kilobytes or megabytes. But say a checkpointing file, like say it's a simulation checkpoint, those could go in gigabytes or even terabytes. So now the thing is, you should not have one common striping config for the entire application, right? So what's a good trade-off is what we are looking at in a per file basis. So we need to see what's a good interception, because there's too much overhead as well per file, right? So we have to have a good way of mitigating the overhead as well as this. Also, the other thing that we are looking at is in University of Tokyo, in your supercomputer, you have, for example, one namespace which is for fast file system, the other namespace which is for slow file system, which is more hard disks, right? So same. So now all of the major supercomputers have a combination of SSDs, hard disks, even like different rotational speeds of hard disks and all of that, right? So the other thing that I'm looking at is, when you're creating a file, can I have the intelligence as to where the file should go? If you're just making, say, a checkpoint file, you need not write it into the same namespace in an SSD, because the checkpoint would rarely be used only in case of failures, right? So maybe it's better suited for a slower file system, right? Where HDDs would, where you have HDDs. Whereas the SSDs would be more useful for, say, when you are running a machine learning kind of an application where you are reading one image file or whatever a lot of times, right? So you are doing continuous reads. So things like that is where a fast file system would help you. So I'm trying to have some sort of an intelligence layer in the middle based on what kind of access pattern was having. So I'm using Darshan to collect all the traces, right? So Darshan is an IO profiler. So I'm doing all of the read patterns, write patterns of all the files. I'm creating a profiler so that we can profile things at real time and make intelligent decisions during the create stage itself. Where should it be created? And how many stripes should we have and all of that, right? So this is the current work that we are looking at. And the initial work, like it's a 4-pager that we gave to the WaitIO workshop itself. So that got accepted. and I'll be presenting it in IEEE cluster about this, but it's a very, very initial stage, right? We don't have the entire pipeline yet. So any questions till here? So that's my one of the works. Okay, cool. So then I'll move forward. So now this work is again slightly different. So here I'm not going into the internals of parallel file system. So this work started when I was doing my postdoc. So where I was in the AIML team, and I was looking at the IO bottlenecks for AIML workloads. So the large scale deep learning applications are typically like this, like where you have some sort of data. And this, I'm talking about the data parallel approach, where you have a machine learning model, a deep learning model, and you have to train on petabytes of data. So now this petabyte of data won't fit in one compute node, right? So what you do is you divide the entire data set across nodes. Say you take 10 compute nodes and you divide the data set across 10 compute nodes. You run like, and you have the entire model on each of those 10 compute nodes, right? And you run this on that partial data set that you have. Then you exchange the weights and all of that, right? And then you shuffle all of these data sets. Then now with these 10 compute nodes, again, the petabyte scale data might not fit. So there needs to be things that needs to come again from the parallel file system in one epoch, right? So one epoch is basically where one round of machine learning model has looked at the entire data set, right? And you, for accuracy convergence, you need to do thousands of such epochs, right? So as you can imagine, in one epoch itself, you are loading the data from the parallel file system to the compute nodes, right? You are doing the training there now, and you are again doing the training on leftover data, whatever was remaining in the parallel file system. Then when the next epoch starts, I think I have one. Yeah. So here I have like, say, a 16 image, like a very small example, 16 image. So after epoch 1, we try to shuffle the data set. Okay. So the data set is shuffled. So then say node 1 will now get a newer set of data so that there is no overfitting and all of that, right? So what that means is, and this happens like across a lot of epochs, right? So that means there is fetching from the parallel file system. There is a lot of data that is being moved across all of these compute nodes, right? There's just too much of data movement that is happening. And this data movement is what makes the entire learning process slower. It's not the number of GPUs or anything, right? It's basically the data movement. And that's why any distributed deep learning process, what we found out is the application spends around 67 to 85% of the time just doing IO. So the compute is there, the communication is there. The communication is where nodes are communicating its weights, it does its forward propagation, the backward propagation, and all of those machine learning things, right? So I'm not a machine learning person. I'm more interested in solving the 60% time that it's solving in just doing IO, right? So that means there's a lot of IO bottleneck that is there in these large scale distributed deep learning workloads. So I had like, so I won't talk about the second one. I'll talk mostly about the first paper. So that was published in cluster two years back. And this was, so the first one is my postdoc work. The second one is more recent. This is last year's FAST. That I was doing it in collaboration with with a PhD student at Virginia Tech. So I'll talk briefly about what Shade does. But so what HVAC, the first one is, what we were thinking is that you are doing the shuffling stage, right? Like after every epoch, you are trying to read data from one node to the other. So how about we create some sort of a distributed cache where we would cache things, where we would do data prefetching of leftover data that would come from the parallel file system, as well as like before even the epoch is happening, like when the GPU is doing its compute, we would take 1 or 2 cores of the CPU to do this data transfer. So compute and the IO is happening side by side, right? And all of this is at the client side. Nothing is at the server. So we were making a distributed cache out of that. And that's basically HVAC. And we tested it in Oak Ridge supercomputer on the Summit supercomputer, and it worked very good. And I think people are using it. Hopefully, that's my postdoc work. Hopefully, people are using it. And the second one is Shade, where we were looking at, like, does every epoch need to be trained on 1 petabyte of data? Or can we get important samples after every epoch so that we can just prefetch only important samples, right? Rather than doing everything. So what we saw is maybe you need more number of epochs to reach convergence. But since you are sampling lesser things every time, your per epoch time goes down, the IO time goes down. You have to take few things, right, in memory, which fits in memory. And overall, it takes larger number of epochs, but the IO time is reduced. And the overall machine learning training time is also reduced. And all of this, I'm talking about training, okay, not inference. So this is distributed deep learning training. Okay. So this is a system design that we have. I have another diagram for how the server and client interacts. So basically, like, you have these TensorFlow, Keras, and all of these compute node libraries, right, that people use for this. So what the compute node libraries that, like TensorFlow or PyTorch, what they do is they call this data loader function to load data, right? Now, this data loader doesn't know where the data is, right? So what we did was we created some sort of an HVAC. HVAC is what I named it. So we have one client side, right? It would just intercept that data loader thing, and we would know what is being called, right? And then we would talk to the HVAC server side to understand where is that image, whether that image is in my system, whether that image is in one of the other compute nodes, or whether do I have to go to the parallel file system to fetch it, right? So accordingly, we were making smart decisions to prefetch all of these. Okay, so it's a rough client server kind of diagram that that I drew. So we were doing everything with RPC calls. So we were using Mercury, the remote procedure calling library, to talk between all of these server clients, right? And the network is basically InfiniBand network. So what we were doing is this, the data loader, it would call some POSIX level call, right, to read. And we were intercepting that using the LD preload library. And then we were tracking files, like what are the files that this particular node wants to use, right? And accordingly, like, we would see whether, like, if we would give it to the HVAC server, there was a queue, a long queue of, like, if you are running on 1000 nodes, your machine learning task, like, there would be a queue, like everyone would be talking to its HPC, the HVAC server node, right? And there we would see whether the file is cached in the local NVMe storage, or is it at the fast file system, or is it at the burst buffer in Summit, or do we have to fetch it now, either from the slow file system or a parallel file system that we have? So the HVAC server would do it intelligently. The client need not worry about it, right? So we just fetch it, we keep it, and we just return the file descriptor which the client wants. So all of this was happening transparently without changing any client code or any server code, nothing. Even like the HVAC client and the server both was sitting at the compute nodes, at the client nodes, right? So nothing needed to be changed. So this is like just one evaluation that I showed for today is, so I'm just comparing the training performance of different epochs. So the first epoch, so as I said, epoch is when one machine learning round sees all the data, right? So since it's epoch 1, that means everything has to be loaded from the parallel file system. Nothing is there, right? So that means epoch 1 would be higher always. right? But subsequently, either the image on which it is getting trained, either it will be in one of the nodes, in one of the compute nodes, it could be in its own compute node, or very rarely would it need to go to the parallel file system, right? So epoch one, a random, R stands for random epoch. Average, like on an average, what did the epoch time take? So what we saw is if we were just pinging GPFS always, right? So Summit had GPFS, the IBM Spectrum Scale file system. So before, what would happen, like before the HVAC system, is if something is not found in its own RAM or on its own NVMe, it would go to the parallel file system. It wouldn't even look at its peers, right? Like the other compute nodes that is doing the same application. It wouldn't look at that. So that's the first, the GPFS thing. The second one is XFS on NVMe. So that's the basically bus buffer. So that's the ideal thing that we want. That means the entire data set is local on its NVMe. Okay, if it fits local on the NVMe, that's the most, like that's the best performance that we'll get. So we want that best performance, right? But the data set doesn't fit in NVMe. That's why we need HVAC, right? So that's the best performance. So that's why the XFS on NVMe is the lowest time that it takes. And then 1x1, 2x1, 4x1 HVACs are basically one client node, one client, one server, two client, one server, four client, one server. So this basically. And what we saw is we were able to scale pretty well with HVAC, right? And the HVAC gives pretty good performance. Like for example, so epoch one, it doesn't matter because everything is coming from parallel file system. It doesn't matter. But if you look at any random epoch or an average epoch time, you'll see that we are considerably better in one epoch time. Like one epoch would take around 100 minutes, but we were reducing it to around 75 minutes, only one epoch, right? So there was a 25-minute gap in one epoch, and there were thousands of such epoch that needed to be run, right? So 25,000 minutes, that's what we were saving on by using HVAC, right? So that's HVAC. And shade, as I said, like I'm not going into details, but it was creating this important samples layer on top of this kind of a caching system. So HVAC is basically a distributed cache that we built real time when a client gives that, okay, I want, the client is running something and it says, I want 10 compute nodes to run. We just spawn out a caching layer across those 10 compute nodes using all of these Mercury HPC libraries and all, right? Yeah, so the current work that I'm looking at in Dash Lab is, so I'm interested in edge computing as well. So there is this concept of federated learning, right? So I don't know if people are familiar with that term. So federated learning is what, like the term was made popular by Google, right? So we all use federated learning daily. For example, I'll just give a very simple example that I keep giving to my students as well. It's basically when we use our mobile phones, right? We type words on the keypad, right? On our Android keypads. And then what we see is like it starts giving suggestions what your next word is going to be when you are typing a message, right? So now how is this happening? So this is happening primarily due to federated learning. So now your typing pattern, whatever you typed, is very private, right? It's a very private data. So your data should not leave your mobile, right? So that means local training is happening at a particular device level, right? But there is some global aggregator that say Google has, for example, for Android, right? So Google has some global aggregator, which, so every night, whatever we did, there was some local training that happened. And then after the local training ended, it sent it back to Google so that everyone who had Android, everyone's only model weights would be aggregated and those model weights would be sent back to you. so that you know, like your mobile also knows from the other mobiles, right? Without sharing data. So that's one thing that I'm looking at from the federated learning point of view is, since all of these local trainings are happening at our mobile devices, right? At our phones. Now, everyone's phone has a different capacity, right? Your phone might have an 8 GB RAM, whereas my phone might have a 4 GB RAM. Your phone might have a 2 GB RAM, right? So everyone's local training time will be different. Everyone's capacity is different. Nodes might fail. Now, I'm looking at all of these with respect to federated learning, right? And as you said, you have some like LLM tasks are being run a lot nowadays, right? So I'm also looking at LLM inference tasks, scheduling LLM inference tasks on HPC clusters. Like not at the training side, because training just takes like so many days, so many hours, right? So Microsoft and all of Google are doing good job at training, but I'm looking more at the inference side, right? So that, say, when you are using Chat GPT or Bard or whatever, right? So when you are typing some question, right, how are you getting the answer back? Because these are also getting scheduled at some clusters, right? So how can we schedule it more intelligently with respect to the HPC side? And there are a lot of so a recent OSDI paper came out. So there is a concept of like token length, and they use KV cache for it. So how can we optimize the KV cache for all of those things? So I'm looking at more on the scheduling side of, say, thousand users are using ChatGPT at the same time. How do you schedule it more intelligently, right? So I'm looking at that point of view from the LLM side. So finally, I would like to acknowledge my students. I have grants from Government of India. I have a lot of collaborators. So these are just the collaborators for my HPC side of things. I collaborate with Oak Ridge, University of Virginia, Virginia Tech, from where I did my PhD. I also have collaborators in Germany. And hopefully, after my visit here, I'll have collaborators in Japan. Right. So thank you. This is our main building of BITS Pilani Goa campus. Please visit. Thank you.
Okay, so next speaker is another title. GPU clusters.
Okay, thank you for introduction. So, okay. So my research background is basically we are moving to the shifting to the GPU computing, so that for the main computing power resource, so that we will introduce the MIABI system in next January, and we are facing the file I/O is actually becomes bottleneck. So because computation time is drastically reduced. So but file I/O still existing. So even if the main part is offloaded to the GPUs. So basically traditionally the GPU memory is also independent from the CPU memory. So usually application run on the GPU have to move the data to the CPU memory when the performing file I/O. So that GPU CPU copy might be overhead. So usually the practical application want to output the snapshot, so in time evolution calculation, and also for AI processing, so input, very huge data set, and also some epoch after some epoch, so the output checkpointing. So and also we have some questions from our users, so that in some cases, so application does not accelerate due to the existing file I/O part. So even their application offloaded to the GPU. So the traditionally, so the file I/O on the GPU should be required so CPU memory copy. So the before the file I/O, so data transferred to the CPU memory from GPU, and but so recently NVIDIA proposed so GPU direct storage, and so this is a part of Magnum IO. And so some kind of extension of the GPU direct RDMA for the file I/O. And so the traditional manner is like this. So for the file I/O, so once the data should be copied to the CPU memory, and also file I/O will be performed by the usual POSIX manner. And so the GPU direct storage is as you can see, GPU memory to local NVMe, so via the PCI Express link directory, or the remote file system like a raster or the BGFS. And basically, this is utilized GPU direct RDMA. So for the like InfiniBand HCA, and so we observed several file I/O performance, and very similar to the MPI case. So GPU direct storage does not always fastest. So some case we need some sorry, CPU memory copy is better than GDS. So we want to switch the transfer method properly. So depending on the situation, like file size or what kind of storage or the write or read direction. Okay, so so in this research, we proceeded two steps. So the first, we observed preliminary investigation of the conditions that improved file I/O performance using some benchmarks, and compare the file I/O performance between the GDS and the CPU copy. And so step two is we designed the framework how to switch the strategy between the CPU copy and the GDS. And so the final goal is automatically select the optimal file I/O method without changing the code of the actual application. So actually, this is the final goal, but the current result is some kind of a manual technique to change the parameters. Okay. Okay, so I would like to introduce some software stack related to the GDS. So as you know, the GPU driver should be installed for the NVIDIA kernel device driver, and also we need file system driver NVIDIA FS, over the NVIDIA driver, and the GDS is available for the ext4 and XFS as a local file system. So actually, of course, we need NVMe SSD. So it's rely on the PCI Express protocol directly. And also the remote FS, including the raster file system, BGFS, NFS, GPFS. So many kinds of remote file systems are supported now. And so to utilize these GDS, so we have to change the code using the CU file, Q file API provided by NVIDIA. So this is some code examples. So traditionally, if we want to read the file to GPU memory, so once the read from the file to the CPU memory, and after that, the could copy from the CPU memory to GPU, like this. So that we need a CPU buffer to read before the transfer to GPU. And so in GDS case, beforehand, we register the Q file handle to the to the CPU side, and after that, directory Q file read can directly place from the file to GPU memory like this. So but quite different manner from the usual POSIX access. This is also quite complicated. So we want to how to easily port from the existing code to the GDS. So fortunately, many applications use the HDF5 and also the NetCDF. Which is also internally use HDF5. So those file IO libraries are very popular for the practical applications. And so recently OSS plugin to enable the GDS on the HDF5 named VFD GDS. So in that case, that we can easily move to the POSIX manner to GDS manner. So in the HDF5, these kinds of functions are provided so that we can easily use. So the user application programmer does not need to change to any more from the POSIX to GDS. That is a very good point. Okay, so this is introduction of the HDF5, and I already mentioned about that. And so as a first step, so we developed some benchmark. So this is very similar to the HackIO benchmark actually, but also this program is benchmark is developed by Miki and my colleague, and so the HDF5 is also used in this benchmark. And so this evaluation is also experiment and performed on the Pegasus system in University of Tsukuba. And so this system has also H100 and also the local SSD and also raster file systems. Okay, so this is also our observation result. So very partly result. So in this case, local NVMe SSD, and x-axis shows the number of n-body particles, and so this is corresponds to the IO block size actually, and so the y-axis shows the bandwidth, and so the upper case is write from the GPU to NVMe SSD, and the lower is so read. And so that you can see the left part shows the GDS result and the right shows the CPU copy result. And so carefully comparison the very small size case. So the CPU copy is better, honestly. And so reverse the bandwidth. And so in larger size, the GDS is better than CPU copy. And so yeah, read case is almost same situation. And so in this experiment, so we use multiple threads. So actually the 8 threads for read in the case of the GDS. So this is much better than the single thread. And so another result on the Rust file system. And so almost same situation for the small block size. And so reverse the bandwidth. And so finally the GDS is better the larger case. And also the in the read case, so the slightly different from the local case that we so the GDS case that so we use so 8 threads that is so better performance than the smaller thread number of threads. Okay, so like that, so that we observed so many kinds of benchmark, so using the various parameters, and so the in summary, that so we could get so these results, and so the categorize so the what kind of strategy is better than a best case. So if the local SSD in the right case, so the small size CPU copy is better, and the larger size is GDS, or this kind of a table we could get. Okay, and so in the second step, so how to apply this knowledge to the GDS plugin. So in the HDF5, so we need to initiate the GDS so that we have to call this kind of function. So we extended this function for the 5th and the 6th argument to provide some hint to the GDS plugin. So like file size and what kind of a file system. Okay, this is a flow chart. So how to decide the strategy. Like so in this case, the example is a file size is 2.5 megabyte and raster write to raster. And so that this is also less than 3 megabyte. And so in that the Rust file system, so we should use GDS, and the block size should be 4 kilobyte, and GDS. Sorry, so should not use the GDS. So finally the newly implemented CPU copy transfer method inside the GDS plugin. So original GDS plugin just only use the GDS. So free use GDS so that we add some new function to utilize the CPU copy transfer method. Okay, so this is a final result. So of course, we need some hint information, but so we could get the better performance. So blue line shows the original implementation of the GDS BFD, and so the orange line shows our modified version. So finally, we could get up to 4.33 times better performance on the local SSD, and so in the Rust case, 6 times better performance for the in that case. So that we change the so three kind of parameters. So so block size and the number of threads, and so the GDS or CPU copy. Okay, so this is a summary. So the GDS performance is not the best case. So the even in the so smaller block size case. So the we improved the performance HDF5 VFD for GDS, so up to about 6 times. And so our future work is so there is so many room for improvement on the so current VFD implementation, like multi-threading support for the CPU copy, and also the introduce asynchronous manner, and optimize the memory allocation. And so the current implementation is so manually hint is provided by programmer, but also some parameter can be automatically guessed. And also our original motivation is a so grasshopper system. And so very recently so we finally get the GDS on the grasshopper system. And so we would like to investigate behavior and performance on the grasshopper. And so very recently we start the collaboration with the Kioxia, SSD vendor in Japan, and also the NVIDIA, so the much more better strategy for the directly from the GPU, so initiate to the storage, so name the BAM and the GIDS. Okay, thank you very much.
Next talk by actually, so he joined very recently. His main mission here is development of CPU. But so today, he will talk about previous enforcing HPC application performance based on graph.
Thank you for the introduction. Good afternoon, everyone. My name is Yao Hu. I'm from the Information Technology Center at the University of Tokyo. Today, my topic is about enhancing HPC application performance based on graph computation. Actually, this topic is more related to graph analytics or graph computation. So, but I think we can come up with new ideas based on the content of this talk. So this is the outline of my presentation. So first, I will make a brief introduction to graph computation and its relationship with HPC. And then I will introduce several graph algorithms like community detection and random walk. And then I will present the idea of node embedding and its applications. And this is actually from the experience of my previous work on graph computation. So finally, I will discuss the future of graph for HPC. So first of all, I will define the term graph used in this talk. So graph is not a picture. A graph is composed of nodes and edges. A node can represent an entity in the graph. It can be a person, a location, or company, or anything you can imagine. And the edges are used to connect the nodes to each other, which can share the same attribute or property. And there are also dynamic graphs where the nodes and edges grow or change over time. So for example, at time t1, the graph is like this. At time t2, and one node and one link is added to the graph. at time Tn, and this node changes connection from this node to this node. So a basic question is that can current state of the graph be used to predict future links? And this can be solved by graph computation or graph analysis. So actually, the graph is everywhere in the HPC, from hardware to application. So from the hardware point of view, the supercomputer network, data center network, memory network, chip network can be represented by a graph where the compute nodes are connected. And from the application point of view, the communication pattern or traffic pattern can be transformed to a graph where the communicating processes are connected. And there are actually many graph algorithms. For example, the centrality algorithm can find the most important node in the graph. And the path-finding algorithm can find the shortest path between the nodes, in the graph. And the community detection can find a group of nodes which are densely connected compared to the rest of the graph. And the similarity algorithm can give you the similarity score of the nodes based on some measures like the distance in the graph. And the embedding algorithm can give you the vector representations of nodes in the graph. And the link prediction can give you the node connection probability based on the, even though they are not connected in the graph. So, so in this work, we use a citation network dataset to construct a graph, which is composed of tens of thousands of nodes and roughly three times of edges. And because the original graph is very large, and here just shows a tiny portion of the screenshot, which shows the relationships between the authors and the relationships between the authors and the articles. And we configure the data set so that 20% of the data are used for test and validation. So here just shows the future co-author prediction result by using different community detection algorithms. And the last one, the COM, shows we combine the different community detection algorithms, and it performs better than any other single community detection algorithm. And this work is actually conducted by NVIDIA. So in this work, the original graph is randomly ordered. So the corresponding adjacency matrix have many non-zeros across the matrix. So this work uses a very simple community detection algorithm to detect the communities in the graph and reorders the processes in each community. So the corresponding adjacency matrix have the non-zeros many close to the main diagonal. So this can improve the cache locality and reduce the communication between the processes. So from the result, we can see the memory traffic and the application execution time can be largely reduced based on the community detection. So next, we look at a very basic graph technique called random walk, which is used in many graph algorithms like the community detection, as mentioned earlier. So the basic idea of random walk is very simple. For example, if we have a graph and we select a node as a starting node, and then we assume a person is standing on that node, and then we move the worker to the next hop. And the selection of the next hop neighboring nodes is random. So for example, if a person is standing on node A, it can walk via the path A, C, B, D, E, H. So the random sequence of A, C, B, D, E, H is a random walk. And the random walk can be used in many applications like the ranking, clustering, communication, community detection, as mentioned earlier, and the node classification and the link prediction. So, so we analyze the random walk process by the use of adjacency matrix and the transition matrix. Actually, the random walk process corresponds to the Markov chains. And this means the next state of the random walker is depends on only on the current state or current position in the graph. So in other words, the random walk process is memoryless. It does not memorize the past experience or past positions in the graph. So for example, if we have such a simple graph, so we can get the adjacency matrix. And then we can normalize the adjacency matrix by column to get the transition matrix. So we can know the transition probability to walk to the neighboring nodes. For example, if a person is standing on node B, so we can see this column. So it has the same 1, 2, 3 probability to walk to the neighboring nodes A, C, and D. And here just shows the simple case. If we assume the different weights for different links in the graph, the probability, the transition probability will be different. And here shows the parallel implementation of the random walk on distributed graphs across servers. And we assume the compute graph data is divided into multiple segments across the servers. So each data segment will be stored in each server for some like privacy or security concerns. So we will need a forwarding table to guide the worker to walk to the next hop server if the next hop is not located in the current server. So here we use two methods, the RMI, the remote method invocation, and the MPI to facilitate the communication between the processes. So for the MPI, and we use the basic data types and basic functions to adapt to different MPI implementations. For example, we use the MPI int array to accommodate the pass information. And we use the MPI send and MPI wait to send the pass information across the servers. And finally, we use the MPI gather to gather the information from all the processes and send the pass information to a master process for the further analysis if required. A very important application of the random walk is node embedding. The node embedding can encode the topological information and generate the node embedded vectors. So by the node embedding, so each node can get the vector representation. And the node embedding can be used for many downstream predictions. And this is because the similarity of embeddings between the nodes can indicate the similarity in the graph. For example, if two nodes are connected by an edge in the graph, they should be close in the embedding space. So next, we can define the node embedding similarity like this. So first, we can generate the d-dimensional embedding for each node in the graph. And the distance between the node embeddings should reflect the similarity of the nodes in the graph. So for example, if two nodes are similar, they should be very close in the embedding space. if two nodes are not similar, they should be distant in the embedding space. So here, for the simplicity, I just use the dot product between the node embeddings to represent the similarity of the nodes. And here shows a visualized example of the node embedding for a famous social network graph. And we can see if two nodes are connected, then they are very close in the embedding space. Actually, and this node embedding algorithm proposed by this work is random walk-based node embedding algorithm, and which is called deep walk. And this is a very famous random walk node embedding algorithm. And so the question is, what is the random walk node embedding? Actually, the main distinction of different node embedding algorithms is in how to define the similarity function. In the random walk node embedding algorithm, the similarity function can be defined as the probability that two nodes co-occur on a random walk over the graph. So the basic idea is that if the random walk starting from node U and visits node V with high probability, and then node U and node V are similar. So the next question is that what strategy should we use for the random walk between these nodes? So a simple method is we can run a fixed length random walk starting from each node in the graph. Another option is like in the work node to web. In this work, it performs a flexible and biased random walk to capture both local and global views of the graph. So the algorithm details will be omitted. So in general, the random walk-based approaches are efficient, but most of them only consider the topological information. So this does not match our application like in the knowledge graph. So in this work, we propose the RVM, and which is a random walk-based node embedding framework on multiplex graphs. And here shows a simple example of the user item graph. Maybe it's hard to see. The user node can represent any entity, and the item node shows the attribute or property related to the user node. And our proposal RVM uses different label information of the nodes to capture both topological and structural information or similarity between the nodes. And based on this graph, and we can construct a multiplex graph by using the user layer information and the multiple item layer information. And on this multiplex graph, and we conduct the biased random walk to capture the within layer topological neighbors and cross layer structural neighbors of a node with adjustable layer weights like the alpha and beta here. So the worker can work within a single layer or jump to another layer with a certain probability. And the most important thing is that the proposed RVM can incorporate various node label information without increasing the computational complexity as the number of layers increases. And here shows the framework of the RVM. The implementation details will be omitted, but the basic workflow, the pipeline is very clear. So first we construct the multiplex graph, and then we conduct the cross-layer random walk, and then we do the node embedding based on an autocovariance similarity method. And finally, we can get the embedding matrix, where each column represents the embedding vector for a specific node in the graph. So in the evaluation, so we use a public global airport network to construct the graph, which are labeled by the countries and the continents. And to visualize the result, and we use the TSNE to reduce the 128 embedding result to two-dimensional data. So, and this shows the clustering result based on the graph choose continent category. On the left is the embedding result by using only the airport information. And on the right is the embedding result by using 50% airport information and 50% continent information. And this, and we can see compared to this one, and this adding the continent information can improve the separation of the nodes. Next, and this evaluate a partial graph with 20% of edges removed. And this shows a similar tendency, adding the label information, that is the continent information, can improve the separation. And the next, and in this case, besides the continent information, and we also add the country information to the embedding model. And because in this evaluation, we cluster the nodes based on the continent category. So the country information can be seen as the noise information. So, and this will lead to the dispersed node embedding result. And this shows a similar tendency when using the reduced data. And also the node embedding result is sensitive to the parameter configurations like the alpha and beta here. And here shows the accuracy of the node classification when compared to state-of-the-art node embedding algorithms. And so from this result, we have two observations. The first, incorporating both topology and the label information can effectively enhance the node embedding performance. And next, second, and the parameter tuning has a very large impact on the node embedding performance. And here shows the accuracy of the link prediction under two scenarios, and one considering all the missing edges, and the other considering the top 10 of the ranked missing edges. And interestingly, and in this evaluation, the considering only the topology information has a better result compared to the other cases. And this is because the link prediction only considers the topological information and takes the topological information into account. So in this case, any blended label information can introduce the noise. And again, the parameter configuration is important in various and different downstream applications. So the parameter tuning would be a very important factor to the node embedding result. And this will be left one of the future works. And here shows several existing works on graph for HPC, including the NVIDIA work, which accelerates the HPC applications based on the community detection. Finally, let's come to the conclusion. So in this talk, I first talked about the graph and its relationship with the HPC. And then I introduced several graph algorithms, including the community detection and random walk. And then I presented the idea of the node embedding, especially the random walk node embedding, including the proposal, our proposal, RVM. So in the future, for my understanding, I think and I believe the graph computation or graph analysis should be a very interesting topic in the for the future HPC developers or researchers. So this is the end of my presentation. Thank you very much.
So final talk today by Professor Shinji Sugimoto, untitled list of the center-wide heterogeneous coupling.
Thank you for interaction. My name is Shinji Sugimoto. I joined this center 2 years ago. Before that, I worked in Fujitsu around 35 years, and maybe then with my cluster, hiring the cluster, and K-computer, and Fugaku, and MPI, and FX, raster-based files. But now I go into my let's go. So my talk is center-wide heterogeneous computing coupling with WaitIO. It's almost same like 47, but slightly changed. Overall, my talk is firstly, maybe you know, you heard from some other with Basic 1 and H3 OpenDX. Then going to WaitIO overview and its application. And next, finally, I talk about the next WaitIO development and JCA quantum project. So let's go talk. So Visual Basic 1 is first real heterogeneous computing. How do you mean? So because Visual Basic 1 is Express, Intel CPU and NVIDIA GPU, and Jasper is for let's say is ARM CPU and different. And here is some system and also, but to use two kind of system is different to two kind of job because these two systems operated by different clusters and also completely different hardware. So we developed WaitIO socket because the connection by some InfiniBand and also two types of shared files. And also we are going to some UTMP, the high-level coupler, using some surrogate model, some HPC and AI, and also we develop a coupling job scalar because two kind of systems are operating different two dedicated job staging. So in this system, we develop coupling job scalar. User just submit two jobs with a special resource decision. So when two jobs submitted, when two resources are available, it's started in real time at the same time. So we developed some open video software platform for the simulation, data, and learning. And there's three types of system: new principle of numerical analysis, standard precision, and also hierarchical data-driven approach. And third one is some system software utilities to use heterogeneous. I'm talking about this third topic. So WaitIO is a very easy application. WaitIO is combining multiple MP applications, but just in the context of bind coupling. And in WaitIO, each application is a parallel block. And in this type of three type of application, and you make a choice. You can choose some process to join the WaitIO group. And after creating a group, you can send them. I send, I receive, and I wait. Just only the same as a WaitIO. I send, I receive, and I wait. It's very easy. But it's difficult to just only. So we give some WaitIO MPI conversion library because WaitIO doesn't have data types. And WaitIO MPI conversion library is very easy to just add WaitIO underscore prefix and function name and data types and operation. So, and you can already easily convert a real MPI application to the WaitIO. Maybe this is part can be set. And I like to show some of performance in the WaitIO socket and WaitIO file, the file read. In Odyssey, in maybe ASE4FX in some commercial version of Gak. Because typically performance is Odyssey is not so good because only 300 megabytes per second. So we developed some WaitIO file because shared file is fast. This one. This is only file. And this blue line is a hybrid because a short message using a WaitIO socket and large message using a file. Mass is maybe randomly protected fast and accelerated by a WaitIO socket. It's very fast. It's good. So let's talk about some applications of WaitIO. This is some heterogeneous computing. One is real-time data processing and simulation. And accuracy for using data filtering and visualization. And also, let's say simulation plus data assimilation. In this case, it's a real-time 3D accuracy simulation. And observation coming here to the accuracy, then the filtering, and then go to send to Odyssey. And on the Odyssey, maybe filtering by via socket. And in the Odyssey, Seism 3D open surface, that's aspect simulation and data simulation. And going back to the accuracy using visualization. I just want to send maybe this kind of stuff is maybe out of the file and share maybe read the file. But in this case, accuracy case, send and maybe this is just to and finally wait. Just one. Just an application in the simulation, NICAM and machine learning PyTorch coupling. This is the atmosphere simulation plus machine learning. For accuracy part, this is a machine learning using PyTorch. Because UTLMP has such an interface. And what I say in the NICAM simulation, this is our MPF portal. So this is maybe which is a machine learning using NICAM data and Maran. It reduces maybe such kind of accuracy part is there. So we are go for the JC project for heterogeneous coupling computing and University of Tokyo Supercomputing. And because of University of Tokyo, we visited and Yuri in the modular supercomputing architecture, MSA. It's a very similar architecture because we aim to realize heterogeneous computing. So we had a workshop in this March, and that's a real workshop because some goal is writing a paper. And we write a paper and accept and present in this September. I talk about some of it. Because some JC are real application, such kind of terrestrial system modeling, platform TSMP, and Chebyshev accelerated subspace eigensolver and brain estimation. So we are going the real application in the maybe. So we are our system to maybe such kind of portability. In this case, we don't have some time, so we have some brain administration. I mean, my case. So our final goal is application portability comparison. Because they are going to operate running on the original TSMP and Maya on their original library in the deep system. And our final goal is this kind of system to go into the implementation of our VDEC1 system on top of the VDEC systems, and we compare the performance and deep and basic VDEC1. So let's talk about some deep system. Deep system a prototype system of modular supercomputing MSA, and they are going to prototype in the deep system. This is a cluster module and a booster and data assimilation module and storage system module. They are going to different types of computation system, and they are going to combine with special some job scale or something like that. And here is some specification module, the cluster module and the booster module. This is 50 nodes and 70 nodes, but is connected by infinite EDR, and maybe cluster module has some two socket, and large memory and memory and also same. But cluster module is one socket CPU and NVIDIA V100. So let's talk about some target Maya. Maya is some CFD application. And Maya, there are some modules, some lattice span, some solvers, and some DG solver, this kind of solver can be coupling, maybe both types. And it's used biofluid, air acoustic, such kind of things. These are so many things. So our experiment goal is MSS simulation for Maya and both systems and the deep end with stereo. And the task is considered performance benchmark the single module, then going to the integrated module interface to Maya without performance deflation. That's it. And Maya consists of solver module and coupler module. So how do you combine this? We think there are two types of system. Because we're using some multi-solver type A, because this kind of FV and DG and such kind of thing. In this case, this kind of WaitIO is used for initialization and data coupling part. And each solver uses each solver and coupling the WaitIO. This is one case. Type B case of one solver is executing multiple systems and almost same as WaitIO. And this is some part of system A and some part of system B. And it's a first type, the lattice span, the post-processing module. So, but currently development and type A initialization part of Maya combated by replacing a member part of it. Because some coupling module is implemented a shared one, so we need to implement some shared one to WaitIO. Type B is a lattice part of written by completely WaitIO function. And now it's some part of starting their work on the GPU. In this case. So let's evaluation the case in the type A. This is only for replacement by initial and coupling module by WaitIO and single module. And maybe a single module and real Intel MPI versus WaitIO. So that's here. And this is and we measured some WaitIO V1 and Odyssey. It's in the WaitIO TOF and also deep system iterated part. So WaitIO runs on real deep system, but also actual source. And here's the result. Maybe it's a process. It's a time by axis. Here's the Odyssey part, and this is a deep system. And in this system, it's very interesting. This is the FJMPI, and this is some WaitIO. Maybe a smaller process is WaitIO faster than real MPI, but in deep system also. I assume because of Maya and MPI in place, and also such kind of MP place is sometimes overhead. Maybe I assume. Next, the type B evaluation is we measure some MPI by type B. Now, we should be the one. And Odyssey and OKS. That means the ARM and Intel CPU plus combine the same application. And the limited learning of some OKS, so we use some of this 128 process, but the Odyssey 64 and OKS 62 process, and then going to some 512 process. It's Odyssey 448 and OKS 64. It's maybe traditional design same, and it's a scale. It's very interesting. It's a real heterogeneous computing Intel and ARM. And next part is Intel part is replaced by GPU. That's the next. Next thing is the WaitIO development of JCP quantum project. And we started this concept last year, and with the Fireball project with Dickensian System, SoftBank, and Osaka University. In this software, we plan to develop a system software, HPC, 2C HPC hybrid environment. And system software, we plan to two kinds of system. One is a QH scheduler, and second one is HC open viewer. QH scheduler is running some type of cost scheduler, but center-wide multiple jobs and cost scheduler on site. This scheduler is currently working on a Fusan, and also I'm in charge of some of HC Vitex on QH. That is an expansion of the WaitIO. So, what is I think I think the WaitIO router. So, in the router, currently working socket and file. That is also good. So, that's a very performance bottlenecks. So, we plan in the center develop high performance communication using RDMA and zero copy routing. Just like LNet router, and maybe with the verbs and with also have been developed, and also we are now ongoing to make a WaitIO router for zero copy routing. And interesting is that among routers, converting RDMA single stream to multiple socket stream, and also such kind of for performance to multiple streams, and also for security with encryption Scrum packet. It's a very maybe challenging project. And here's with a software architecture, this kind of figure. Before that, this is a socket and file, but we added some RDM type. And here's a summary performance. And wait above to material and accuracy. And compared with a socket. And latency, here's the message size and megabyte microsecond. It's 1/10, maybe 10 times faster than with a socket. And for bandwidth, it's with a socket, but it's 4 gigabytes per second, and maybe accuracy has a 4 layer, and one layer 24 second, 24 gigabytes per second. Using a 4 links, it's a 8 place maybe coupling. In that case, maybe almost 96 gigabytes per second. It's very fast. And also we have a system Mercury that InfiniBand is replaces NDR 400. In this case, up to 191 gigabyte by using 4 link. It's very fast link. And also we developed some WaitIO TOFU for this. Actually, WaitIO socket bandwidth is very low, 222 megabyte. But using WaitIO TOFU, it's increasing up to over 6 gigabytes per second. And latency maybe 10 times fast. And I show some WaitIO Python interface of WaitIO. It's easily some communicate interaction and Python program directly. It's many of quantum computing use Python-based tools. So solution is just providing WaitIO Python interface. In this case, this kind of stuff, maybe one is with 2 types of system, MPI application, and 2 types of this Python application. Maybe you can join for application by using WaitIO. And here is some Python application from interface. And because some data exchange of Python interface and WaitIO library, we prepare a cross object, WaitIO group and WaitIO rank, WaitIO size, WaitIO request. And also we use some connection buffers using NumPy. And the function is almost same cheap, pure limited. Yeah. It's maybe only object here and some of 2 types of initialization function. After that, and wait, I send, I receive, wait only.
bridge.
So here is rest of the talk. Thank you very much.
This is the end of the program. And thank you very much for joining, so even for online. And the next ASE meeting will be October 10th, but it's in Japanese. And this time it's something like a tutorial, creating physics, info. And also the 50th, the next one will be early November. So it's a 50th anniversary. It's a panel discussion. Okay, so yeah, we continue this activity, and we have some good speaker from outside. Thank you very much. Thank you very much.